We all want a cleaner, greener future, and a big part of that is how we store energy for things like electric cars and power grids.
Traditional batteries use liquid electrolytes that can leak and cause safety issues. That's why scientists are so excited about a new alternative, gel biopolymer electrolytes, or GBEs.
Gel biopolymer electrolytes. That sounds complex. What are they made of?
It's simpler than you think. They use biopolymers, which are natural materials derived from renewable sources like agriculture, waste, or seaweed. Think of them as eco-friendly plastic.
What kind of natural materials are we talking about?
The most common ones are chitosan from crustacean shells, cellulose from plants, alginate from algae, and starch from corn or wheat.
That's amazing. Using waste products and plants to build better batteries. Why are these materials so suitable?
Besides being abundant and biodegradable, their molecular structures are great at helping ions move around, which is essential for an electrolyte to work. To turn these biopolymers into an electrolyte, they undergo a process called gelation. This transforms the biopolymer solution into a gel-like matrix that holds the electrolyte liquid.
Table 1 compares different biopolymers. I see they have different conductivity levels and are used in various applications, from sodium-ion batteries to flexible electronics.
Right, and the way they are processed, like through cross-linking or blending, really affects their final properties.
How is this gelation process done? The diagrams here show a few methods.
There are two main ways, physical gelation and chemical gelation. Physical methods, like solution casting or electrospinning, use non-covalent bonds to form the gel. Chemical gelation, on the other hand, uses methods like chemical cross-linking or in situ polymerization to create strong, covalent bonds between the polymer chains.
So, what's the difference in practice?
Physical gels are simpler to make and more flexible, which is great for disposable devices. Chemical gels are much more robust and stable, making them ideal for high-performance, long-life batteries.
And how do the ions actually move through this gel?
It's fascinating. The polymer chains are constantly in motion, which allows ions to hop from one spot to another, almost like they're jumping through the molecular structure. Scientists use techniques like X-ray diffraction, or XRD, to analyze the structure. These graphs show that a less organized or more amorphous structure allows ions to move more freely, which increases conductivity.
What about the chemistry? How do we know the materials are interacting correctly?
Techniques like FTIR and Raman spectroscopy help with that. The peaks in these spectra confirm that the polymer, salt, and other additives are forming the right chemical bonds for efficient ion transport.
So we know the internal structure is right. What about the overall texture?
That's where microscopy comes in. Images from scanning electron microscopes, or SEM, show that a smooth, uniform, and porous morphology is key for good performance.
Battery safety is a huge concern, especially with overheating. How do GBEs handle high temperatures?
That's a great point. Thermal analysis shows that we can add inorganic fillers, like tiny ceramic particles, to the biopolymer matrix. This greatly enhances their thermal stability, making them much safer. As you can see in Figure 9, adding fillers can significantly lower the glass transition temperature, which means the polymer chains become more flexible, boosting ion mobility and conductivity.
So they're safe and sustainable. But do they perform well? How is performance measured?
A key metric is ionic conductivity, which we measure using electrical impedance spectrometry. The goal is to have very low resistance, allowing ions to flow easily. Figure 11, called a Nyquist plot, helps us visualize that resistance. A smaller semicircle on the plot means lower resistance and better conductivity.
Another critical factor is the electrochemical stability window. This tells us the voltage range a GBE can operate in without breaking down.
While biopolymers often have a narrower window than synthetic ones, researchers are developing hybrid systems to improve their durability.
Okay, so GBEs are proving to be a promising, eco-friendly option for future energy storage.
They absolutely are. From supercapacitors to lithium-ion, sodium-ion, and even zinc-air batteries, these sustainable materials are showing incredible versatility.
It's amazing to see how material science is turning natural resources like algae and starch into high-tech solutions.
While there are still challenges to overcome, gel biopolymer electrolytes are paving the way for safer, more sustainable, and higher-performing energy storage for everyone.